Hi, everyone. Thank you for having me. I'm Jonathan Sukovich from the University of Michigan, and today I'm going to be talking about transcranial histotripsy dose monitoring via acoustic cavitation emission feedback methods. So just a little background. Histotripsy is an ultrasound therapy that uses short duration, high amplitude pulses to generate targeted cavitation to mechanically fractionate tissue. And it's being investigated for a number of applications in the brain, included for microbubble-mediated drug delivery, BBB opening, and volumetric tissue ablation. And it's for targeting a wide array of indications for tumor treatments or stroke treatments and neurological disorders. And we've previously demonstrated that we can accurately target histotripsy to about 1.5 millimeters through the skull and achieve high ablation rates upwards of 2 milliliters per minute transcranially. But dose monitoring is important for any transcranial or brain application because you really need to be able to ensure that the tissue that you're trying to destroy is 100% destroyed by the end of treatment. And there's a couple methods that can do this currently, like MRI or passive cavitation imaging or acoustic cavitation emission methods, but they're generally not fast enough or sensitive enough for doing this in real time. And so you might ask, why not just overtreat everything? We know that if you deliver enough pulses to something, histotripsy pulses to something, it'll eventually be fully destroyed. And the reason is that for volume targets, you have to steer the focal point of the array through a lot of different points to fully ablate the entire volume. And usually that's upwards of 1,500 points per cubic centimeter. And we also know that the susceptibility of different tissues to cavitation-induced damage differs. So there's no one-size-fits-all treatment level that'll ensure 100% damage in everything. Another issue is that we also, in addition to monitoring the induced damage, we also have to monitor the spatial damage. So if you're targeting a large volume, you need to make sure that every part of that volume is fully ablated. And localization, cavitation localization via current methods, it's often in the neighborhood of 70 hertz, but in order to achieve high ablation rates, we have to use a high treatment PRF, upwards of 100 hertz. So what we really want to do is develop methods that will allow us to both monitor the level of induced damage as well as monitor it on a per location basis at the rates that treatment is delivered. And so you might ask, well, how do we plan on doing that? And if you think about how damage generation progresses in histotripsy, it gives you kind of an idea. And so what happens during histotripsy is that cavitation incrementally destroys the tissue and reduces it to a liquid. So after one pulse, what you see here in the brain tissue is a pockmarked lesion, but still mostly intact tissue. As you increase the number of pulses, the lesion gets more uniform and filled in, and eventually it just becomes a uniform lesion volume. But when you do that in a volume, you can see that at the end, if it's fully ablated, you have this liquid homogenate that you can evacuate. And so we can say that this changes the material properties. Initially, it's a viscoelastic solid, and then it just turns into a viscous liquid. And that gives us perhaps a way to monitor induced damage. And how do you do that? Well, if you think about how cavitation dynamics depend on material properties, we've previously shown that in stiffer materials under otherwise equivalent nucleation conditions, the maximum radii of bubbles are smaller than they are in weaker tissues. And the lifespan and the dynamics of those bubbles are more rapid in the stiffer tissues. So it's reasonable to assume that in a stiffer or intact tissue, the lifespan should be shorter, but as you liquefy it and it breaks down, the lifespan should get longer. So by monitoring the lifespan, we should be able to monitor at least the material state of the tissues, which we can then use to assess damage. And so then you might think, how do you do that through the skull? Because it's opaque. So the answer that we came up with is acoustic cavitation emission signals. So we know that during the expansion and collapse of a bubble, they emit shock waves, and you can measure these shock waves, which would then tell you the cavitation lifespan. And we've previously demonstrated at least that we can measure the cavitation nucleation signal through the skull to do cavitation localization, but the old transmit-receive capable histotripsy array we had wasn't sensitive enough to monitor the collapse signals. So we've since updated our histotripsy arrays, and now it's got the sensitivity to see the nucleation ACE signal, the collapse ACE signal, even the rebounds of the rebounded collapse bubbles. So now we can measure the cavitation bubbles' lifespans during treatments, which would hopefully let us monitor induced damage. And so we wanted to see if we could use these ACE signals or monitor these ACE signals and correlate them with the level of induced damage in tissues that we treated in experiments. And so in these experiments, we used this 360 element, fully transmit-receive capable transcranial histotripsy array that you see here. It had a center frequency of 700 kilohertz and a peak pressure output in the free field of about 600 megapascals. Each one of these array elements is attached to an ADC, a 12-bit ADC with a variable sampling frequency, so it can monitor those ACE signals. and then it can communicate those ACE signals and measured waveforms back to the host computer via Ethernet. And so in the experiments that I'm going to describe, the setup is basically exactly what you see here. We have this 360 element transcranial histotripsy transducer. We mount a skull in it at the through the focus, and then we mount a tissue sample embedded in gel at the center of the skull at the array's focus, like you see in this case. So in the experiments, we wanted to look at how the ACE signals change as a function of different tissues. So we delivered treatments to different bovine tissues through the human skull, including brain, liver, and blood clots. The focal pressure during all treatments was approximately 60 megapascals and constant for all of them. Pulses were delivered at a rate of 200 hertz. Treatment was delivered through a 1 centimeter wide steering volume made up of about 1,500 points. And to generate different levels of induced damage at the treatment endpoint, we applied 10, 30, 100, or 300 pulses per location in each of the samples. During all treatments, ACE signals were acquired after every pulse. The whole signal duration was about 800 microseconds, and it was acquired at 5 megahertz sampling frequency. And this was with all 360 elements of the array. Induced damage following treatment was assessed histologically via an H&E and staining. And then afterwards, we would look at which features of the ACE signals correlated with the histologically assessed damage. And we were specifically looking at the cavitation lifespan and amplitude of the collapse signals. And so here's some results. The histology, what you see here are the histology of brain and liver samples treated with 10 pulses, 30 pulses, and 100 pulses. And in the 10 pulse case, you can see in both the brain and liver, while there's clearly damage in these regions over here and intact tissue off to the right, there's still intact pockets of cells in this damaged region. And in fact, you might say it's more pockets of complete destruction surrounded by intact cells for the most part. After about 30 pulses in the brain tissue, there's basically no brain cells left in the treatment region. And you can see there's sharp boundaries between the treatment region and the damaged region. In the liver is a little bit tougher, so there's still pockets of residual cells throughout this 30 pulse treatment zone. But after you get to 100 pulses, pretty much all the cells, brain and liver cells, are destroyed, which you see off here to the right. If you look at the percent of necrosed cells within those volumes, what you see is that after about 10 pulses, there's still a lot of intact cells left in the damaged region. But once you get to about 30 pulses in the brain, at least, you're generating a lot of damage, less in the liver tissue. But after about 100 pulses, you're at about 90% damage or above. So then we look at the cavitation lifespans, and what you see here is just a sampling of how the cavitation lifespans evolved in the brain treatments. And what you see is, like as expected, early in treatment, the cavitation lifespan is shorter when the brain is still intact. But as treatment increases, the lifespan increases, and then it eventually plateaus. At some point, you can't damage the tissue anymore, so the lifespan shouldn't change anymore. And the plateau happens at about 30 pulses, which agrees with the necrosis slide you saw above. In the liver, it's a little bit different. And this is a handful of pulses or a handful of treatments from the same liver sample, so the same animal. And you can see that while the same trend exists, cavitation lifespan starts small and then increases and plateaus, it changes differently for each sample. And it's not always even monotonic like you see in this one here. And you can see that it still tends to be increasing at 30 pulses, but it kind of levels off at 100 pulses, which is about where the 100% damage was in the necrosis based on H&E. Looking at the amplitude, it's even a little bit more silly. What you see here is that it's not necessarily monotonic. This is for the liver samples. It increases, then decreases, then increases, and plateaus again. And it behaves differently for each sample. And we were interested in why this is. And if you go back to the histology and look at it, what you end up seeing is that in the cases where you do see those non-monotonic behaviors, you get a lot of residual structural tissues like portal tracts and blood vessels, whereas when the amplitude plateaus, you don't necessarily see that. So we think that that's why that happens. And so that's about it. Right now, it seems like the cavitation lifespan correlates best with the percent necrosis or clot liquefaction in these tissue samples, where the plateau is indicative of 100% necrosis. And the rates change based on the tissues. And we think that the significant variation across samples in the liver case is just due to the presence of those residual structures that don't really exist in the brain. We've observed that the trends depend on treatment parameters. So we saw those jagged lines Those are likely due to residual bubbles that don't have time to dissolve between pauses in treatment. And another limitation of this study was that the dose spacing was too large. So we only really effectively generated 2 damage endpoints. So we aren't able to quantify what the level of damage is necessarily, except for 100%. And with that, I would like to acknowledge everybody and thank you for listening.